In this chapter, we're going to cover of the various aspects of testing objectives and philosophy. What are we trying to do? What are some simulation concepts that we might use in the vibration and shock world? How do we assess environments? What are the damage potentials? What's going to break our specimen when we test it or in service? How do we specify tests? What are MIL standard testing? And then some side issues such as experimental stress screening, highly accelerated stress screening, and other associated testing strategies that you might use. Okay, why do we do tests? There's a variety of reasons. One of them is fundamental experimentation and research. One of the examples that I use for that is testing of wind turbines. And what we're doing there is putting up a wind turbine and perhaps in an area where there is a lot of wind, and then we wait for the wind to come along and we measure the response of the wind turbine and see whether it is what we expect. Another possibility is specimen or material system characterization, stress strain tests, and one that's in the vibration world is modal tests, where we're trying to come up with a mathematical model of the specimen under test. What we're going to talk about in this section, though, is proof and qualification and acceptance testing, and proving that a device that we're manufacturing will work and is going to work with future models of the same thing. Performance assurance, quality assurance, qualification testing. So what the objective is to be as sure as possible the test specimen will survive the expected use environment without sacrificing a significant part of its useful life. So this is a tightrope that we have to walk to be sure that we aren't damaging the specimen, but putting enough stress on it so that we can assure that if it is going to fail in service, it will also fail in our testing program. An old quote from Wayne Tustin in 1986 is that we learn little from our successes, failures can teach us more. And the fundamental problem here is that we have to design a test that is going to produce failures if we're going to have failures in service. And this is a tough job. But the whole point here is that we want to design our test for failure. That's got to be the objective of the test, regardless of what the customer thinks. If we don't design for failure, that means that we're never going to find a failure that might catch us in service. If the test is designed for success, why do it in the first place? It's going to pass no matter what. So we're going to talk about three kinds of testing, and specifically what I'm going to talk about is how things are done in the aerospace industry, but other industries do similar things, and I'm going to ask you folks all to interpret this in a way that makes sense for what you're actually doing in your particular industry. So in the aerospace industry, we go through qualification testing that's done on the prototype in the development stage. Acceptance testing is done on the first few delivery items, and then if we're building a lot of the same thing, screening is done on all delivery items. So let's talk about those things one at a time. Qualification testing is proof of concept, and it's performed during the development cycle as early as possible. The levels of the testing are the worst expected case. The objective is to expose design shortcomings and errors and protect the builder and the vendor. So what we're going to do is apply an environment, see if the specimen operates or survives, And if it doesn't, first of all, check to see if the test is valid. Make sure that we're not over-testing the system. If the test is okay, we're going to analyze the failure, enhance the procedure and the product, and then retest. An example of this, which is sort of an unusual one, is this is a picture of the prototype of the Hubble Space Telescope that we built at Lockheed. And what it is a couple of cans that look sort of like the Space Telescope. And here the primary mirror is right in this section here. The secondary mirror is up here. And these were simulated with big aluminum plates, and we put accelerometers on those plates and shook the specimen with little tiny shakers that were down here in the area of the control moment gyros. And the objective here was to see whether when we were exciting the specimen with a few pounds of force, whether we got acceptable motions or whether we got smaller than acceptable motions here on the two mirrors. And so the success in this particular test was to find out that the mirrors did not move too much when we excited the specimen with a low-level excitation. What we're seeing here is a very early computer system. This was in the late 1980s. This is the first data acquisition system that was capable of acquiring 200 channels at 10,000 samples per second and continuously. And so what we're seeing here is two significant pieces of history: a computer that was the fastest of its time, and this specimen, which now, if you've been to the Smithsonian Institute and seen the Hubble Space Telescope, that is not the Hubble Space Telescope. It is actually this set of cans, and that's been dolled up with all of the pieces that are on the Space Telescope itself. So this is a piece of history that you can see today. Acceptance testing. Again, the Hubble Space Telescope, and acceptance testing is performed at delivery. The levels are nominal. We don't want to break our specimen. The objective is to prove operational capability and protect the customer. So what we're going to do is we're going to design a test. And one of the fundamental problems here is that most of the testing programs that I've been involved with, the test is designed by the builder and approved by the customer. And this is certainly not the way it ought to be done. This is the fox watching the hen house, and the customer should certainly be very strongly involved in designing the test. We're going to apply the environment, see if the specimen survives. And in this particular case, what we see is the Hubble Space Telescope, and here you can see all of the pieces on it that are similar to the ones that you see in the Smithsonian Institute. And what these Hubble Space Telescope here is being put into Lockheed in Sunnyvale's high-level acoustic chamber, and the objective here was to subject the specimen to the acoustic levels that are subjected to the specimen by the space shuttle, and make sure that it would survive that in the actual launch. Screening is performed on each delivered item. This is obviously set up for mass production. The levels are designed to precipitate failures that are caused by manufacturing faults, and we'll talk about that more later. The objective is to provide the ability to prove the ability to survive in service, protect the customer, and primarily to protect the builder against returns. Of course, a return is a pain for the customer, but it's an expensive thing for the builder. So we're going to design a test, apply the environment, see if the specimen operates and survives. If not, we're going to fix the individual device before we ship it out. So an example here is a thermal chamber where electronic devices are being tested, and they're also being shaken by a random generator down here in the bottom. So we get a combination of random excitation and thermal excitation to make sure that the devices will survive. More about this later. Okay, so the question is what's the environment? We've talked a little bit about the environment that's in the typical one in the aerospace industry, where we have a cargo in the space shuttle. Let's say it's the Space Telescope, and it is subjected to all kinds of excitation during launch from the solid rocket boosters and from separation of the devices and all of that sort of stuff. Lots of random, lots of acoustic, lots of dynamic excitation in general. Helicopters have a largely cyclic loading due to the vibrations of the rotor, and also if it's a military helicopter, it might be subjected to gunfire and all sorts of other nasty environments like that. So those are things we might want to simulate there. If we're in the automotive industry, we have a potential for having collisions. We obviously have to worry about going over bumps, a lot of different excitations that we have to cover and make sure, in particular, for instance, that the passengers will survive some sort of a crash that looks like this. So we're going to apply an environment. The philosophy is that the testing environment should include all of the expected environmental conditions: temperature, humidity, vibration, shock. But the fundamental problem is that in a test lab we really can't do all of these things simultaneously. So here's an example: the launch of the space shuttle, and our cargo is here in the cargo bay, and it is being subjected to very high level acoustic and environmental and vibration. There are secondary environments. As the system lifts off, the pressure changes as we go from atmospheric pressure to space, where it's vacuum, and also the temperature is going to change as we go. And one of the questions here is, what's important? What do we really have to test for? Do we have to test for all of these things at once? And the answer to that is that would be a really good thing, but we're probably not going to do that. Another possibility is shock environment. Once the Space Telescope or other spacecraft is launched, there will be events in orbit. For instance, deployment of the solar arrays is normally done with a small explosive device, a pyrotechnic device that pulls a pin and releases the arrays. So this causes significant shocks, high frequency shocks, and that the electronics and other things that are in the area of the explosive have to survive. Again, the secondary environments are pressure, in this particular case vacuum when it's already in space, and temperature, which is going to be cycling depending on where we are in orbit, whether we're in the Earth's shadow or not. So how do we do this? The environment, in most cases, the environment cannot be reproduced completely. So how well do the real conditions need to be reproduced? And what we need to do here is use our experience and guesses. How well can the real conditions, or even parts of them, be reproduced? And so that's the topic of the next few slides. For this course, we're going to restrict ourselves to the structural dynamic aspects of the environment. Doesn't mean that other conditions are not important, but there's enough considerations here for us to worry about to keep us busy. So we're going to be discussing vibration and shock, and there's lots of cases where damage might happen depending on what's going on with our specimen. There might be damage due to accidents, drops, and other unexpected inputs. And of course, this is important for the computer industry when the devices or the printers or the computers or laptops are being delivered. There's a significant chance that the carrier is going to drop the device, and it would really be good if it will survive that. Another one is anticipated inputs. Automotive road vibration is fairly easy to characterize for specific cases, and one of the examples here is a Belgian block road where you might drive your car over a bunch of bumps and then simulate that excitation on a shaker later in your laboratory. And we also have a pretty good idea of what the environments are for aircraft and spacecraft. And aircraft are the primary thing there is that we have to worry about is fatigue damage. And we understand, and what we do is we subject our aircraft to a long fatigue test where we're, for instance, bouncing the wings up and down for a long time. Okay, the relative importance depends on the application. Accidental inputs are the main concern for most commercial products, computers, etc., and cars. Anticipated inputs are the most important in aerospace applications because we've got a pretty good idea of what the environment's going to be. Some applications worry about both. Automotive is the main place where we have to worry about both accidental and anticipated inputs. So, in the vibration world, how are we going to simulate these things? Real vibration environments are complex, and the vibration inputs on a component include 3 translations, X, Y, and Z, 3 rotations around X, Y, and Z, and there's another set of degrees of freedom which you don't think of immediately, but the boundary conditions that our black box is mounted on are going to apply bending loads to the structure that are shown here in this with these arrows. And it is important that we emulate the boundary conditions correctly, and we'll talk about that a good deal when we talk about shaker testing. Should the box be mounted on a rigid table, or should it be mounted on something that's soft, that emulates the real mounting conditions for the box? But anyway, for the moment, what we worry about is that each of these inputs has its own time history and spectrum, and the question is can the complete environment, just the vibration environment, be simulated? So the standard method of simulating the vibration and shock motions is repeated single direction tests. Drive it in the vertical direction, drive it in the one horizontal direction, and drive it in the other horizontal direction. And the question is whether this is a good enough simulation of the real environment, which is 6 degrees of freedom or more if you look at the past slide. So the question is what's realistic, or what is actually going to cause the damage to our specimen? Can we get away with 3 uniaxial tests, or do we have to do a multiple degree of freedom test? And one of the cool things that's going on in our industry right now is that multiple degree of freedom testing is coming into its own, and we really can do 6 degree of freedom tests. So what we want to do is produce a realistic environment. How do we do it? What's realistic? Can the damaging environment be realistically reproduced? And the answer is sometimes. If not, how do we model the environment? How do we reproduce the damage potential of the real environment? So, real world's full of hazards that need to be survived. The producer wants to be reasonably assured that his product performs adequately, and the examples of that are launch loads, fatigue and impact loads, shipping loads on computers. Is the computer expected to work when it's dropped or has coffee spilled on it? And the answer to that from our user standpoint is obviously yes. Okay, does it need to survive shipping, road, and minor collision loads on cars? What's the damage potential of these environments, and how do we simulate them in the real world? So what makes things fail? Fatigue. Failure happens after a large number of cycles. This is one of the main things that the aircraft industry worries about. The wind turbine industry worries a lot about this. Another one is overstress, impact or transient loads, or in the case of wind turbines, a wind that is stronger than is expected. Another possibility is over travel, unacceptably large motions. The example there is the space telescope, where there might be too much vibration on the mirrors due to control system inputs. Another one is interference, colliding parts, that if things move a lot in your structure, they may collide and break each other. The opposite of that is disconnects, intermittent electronics, where vibrating and a connector intermittently disconnects during the vibration. And then we might have combined environments where thermal stress will exacerbate the vibration conditions. Okay, first thing we'll talk about is fatigue. The SN curve, stress to number of cycles curve. And the point here is that fatigue damage is highly dependent on the stress level, and this is an SN curve for brittle aluminum. What we're seeing here is on the vertical axis is stress, horizontal axis is life in number of cycles, and what we're seeing here is that at high stress, 320 or on the order of 300 megapascals, we have a very short life, 1 cycle. At low stress, we wind up out here at 100 megapascals. We wind up having a life that is 10 million cycles, essentially infinite. And as the stress gets lower and lower, we will reach the fatigue limit where the material will last forever. So obviously what we want to do is, if we have a specimen that is going to have to operate for a long time, like an airplane, what we're going to do is want to set our test up so that the loads on the specimen are similar to what we expect in flight, and then test it for a long time and see whether it survives. And one of the interesting tests that I saw probably in the 1980s, early 1990s, was the Lockheed transport plane, L-1011, being cycled in Lockheed's lab in Southern California. And the objective there was to keep cycling it so that it was well ahead of had a whole lot more cycles than the planes that were in the fleet, so that a failure would be spotted before the fleet machines, the fleet airplanes got number of cycles. Overload damage caused by one or a few cycles, shock testing. And we might have an impact test or a drop test that stresses the specimen with a time history that looks like this. And failure is exceeding the yield stress capability of the structure. And if that's the case, it's bent. exceeding the ultimate stress of the structure, then it's broken. Perhaps we'll have an intermittent disconnect where during the shock the device stops working, or perhaps we have unacceptably large deflection due to the shock. Interference. Parts may collide and damage themselves, and I'm going to show you a movie about this where we are driving a specimen in the vertical direction, and we have two beams on the that are mounted on the block, and what they do is they vibrate, and the when the conditions are right, they will actually collide. So let's bring in that movie.
My goal is to show you the vibration responses of the two cantilever beams you see mounted on the shaker. This graphic approximates what we've mounted on the shaker, a block that clamps two cantilever beams having different thicknesses, different natural frequencies. Note that the beams are inclined by 45 degrees from the shaker axis. The beams will respond to that component of shaker motion that is perpendicular to their least dimension. First, we will drive the shaker with a 5 Hz sinusoidal signal. At very low forcing frequencies, the entire load moves with the shaker. Transmissibility equals 1. There are no resonant effects. But as we rise in frequency to about 22 Hz, we see that one beam begins to resonate. We'd better reduce the electrical power to the shaker. There's another resonance, this time at 34 Hz. Again, if we were to dwell at 34 Hz, this beam would eventually fatigue and crack. However, fatigue is not our goal. Let's move rather quickly upward in frequency. Beyond 36 Hz, there are no significant responses. How shall we define failure for this particular test? I propose that we define failure as striking together of the beams. Now we'll excite our model with random vibration. The two reeds represent two circuit boards. With a broad spectrum motion from approximately 0 to 100 Hz, we find that the reeds occasionally strike each other. Note that the response doesn't change when higher frequencies are added. The reeds are unaffected by the higher frequencies. This model exhibits a failure mode with the reeds simultaneously excited, a failure mode that didn't occur with the reeds sequentially excited. We're driving the shaker with a broad spectrum signal from approximately 0 to 100 Hz, and we're illuminating the two-reed model with a strobe light flashing at 22 Hz. This enables us to quite clearly see the 22 Hz response of the red beam. Now let's run the strobe light frequency up to 34 Hz so we can watch first mode resonance of the white beam, the thicker beam. And that first mode bending resonance is quite clearly seen.
Okay, now there are several things that we've seen in this movie. First of all, this problem that I'm talking about here of interference, what we saw was that when the conditions were right with a sinusoidal test, we got a whole lot of motion, but we didn't get hit. We didn't have any interference. However, when the experiment was run with random, we got hitting on a fairly regular basis because there were frequency components in the test that excited both of the beams. So there's a couple of important points here. One of them is it really matters what excitation function we use. If we were doing sinusoidal testing, sine sweep testing, this would not have produced a failure of the type, of the interference type, but if we test with random, then it very definitely did produce failures. So, fundamental question here is, when we're doing structural dynamic testing, do we want to use sine or do we want to use random? And in this particular case, we obviously want to use random. However, there are some other cases where we very definitely want to use sine. It depends on what kind of failure we're actually looking for. Another possibility is intermittent failures, intermittent disconnects, and this is a problem that I have actually run into. What I've got here is an accelerometer with a microdot connector on it right here, and the problem here is that we got some cables that had an oversized pin in it, and this worked fine until we disassembled this and remounted the accelerometer and hooked it up with another cable that had the pin that was the right size. And what had happened is that the female part of the connector here had been expanded by the oversized pin on the cable, and so what happened is that when we put the correct cable in, we got intermittent disconnects right here. Needless to say, this is going to fail right at the maximum acceleration or near the maximum acceleration that you're seeing. So obviously this would have corrupted the test that we were doing. So there are two testing philosophies, two fundamental concepts that are used for vibration environment definition. One of them, the first one, which is the one that I've been involved with most of my life, is environmental simulation. So the objective here is to provide an accurate simulation of the expected environment as possible. And this is appropriate when the environment is fairly well defined, as in spacecraft, launch and flight. The problem with this is that actual simulation of the environment is relatively expensive because it requires programmable shakers and excitation systems that actually do precisely what you want them to do. The other possibility that has become popular over the last 30 or 40 years is stress screening and extensions of that. And this is to apply an environment that is designed to precipitate service failures before delivery. So it's a harsh, conservative environment. It's used when there's a multitude of service environments and returns are prohibitive, as in the computer business. And here, this is failure stimulation as contrasted to failure simulation. So let's talk about environmental simulation first. It's based on empirical data, and what we want to do is design a specification, and to do that we have to have data. So what I've got here is a time history from some sort of a shock, and I've calculated its, this looks like the Fourier spectrum of it. And it would be good if we had a lot of tests, or at least a lot of engineering experience, or preferably both. So let's say that we had 4 experiments, and where we hit our specimen or our prototype with 4 different excitations, or we had measured 4 different excitations from flight or other input. So how do we design a test excitation that represents the damage potential of this data? Okay, first of all, one possibility is to build a time history that envelopes the measured data. So what I'm going to do is I'm just going to take all 4 of these time histories and put an envelope around them, and then The question is what time history should be inside the envelope. And the critical thing here is that there's a lot of empirical evidence that indicates that the most important structural damage reproduction parameter is the frequency distribution of the data, whether we're hitting resonant frequencies of the specimen. If we are, then the specimen's going to take off and potentially fail. So for this example, what I'm going to do is calculate the power spectral density of each of the time histories, and those all look like these here. Other possibilities are shock response spectra, lots of other spectral calculations that we talk about in other parts of this class. So what we want to do then is to envelope the spectra. And one of the possibilities is this: just get out our fat pen and draw a line around that covers all of the possibilities. What's wrong with this? Obviously, this is an overtest. Everywhere where the purple line is above the envelope of the actual inputs spectra, this is going to be an overtest. And this is obvious here, but here is another spot right here, right in this frequency range right here, where the specimen obviously doesn't want to go. And so this is a particularly nasty overtest. So one of the possibilities is to make up a spectrum that follows the envelope really well. And the closer I put it, the less severe the test, the less severe the overtest. But on the other hand, I only have 4 tests in here, 4 data sets to match, and I may not have gotten one of the worst cases. So this is an art rather than a science, and but the bad news is it's the best thing that we've got. So anyway, if we want to find a time history from the spectrum, the spectral magnitude alone, which is what we drew on the last slide, does not define the time history properly. In fact, this particular spectrum has these 3 time histories, and in fact, it has an infinite number of time histories, all that have the same spectral content, but very definitely don't have the same time history, very definitely don't have the same damage potential. So what we want to do is make up a time history that has a representative conservative time history envelope, something that looks like this, and a representative spectral envelope. And of course, both of these are going to be conservative. Being conservative is a good thing unless it results in an overtest, and then it's not a good thing. And so the question is how we're going to make these things up. And of course, what I've shown you here is a transient. We also have to make up excitation functions for random and sine and other excitation functions that we might want to use, and we will talk about those in future chapters, and the transient, random, and sine testing chapters that are yet to come. Okay, just briefly, where do specifications come from? Where, if we don't have a clue of what we're doing, what are we going to use for our standard spectra or standard time histories, or whatever you want to call it? And the MIL standards are a set of standard spectra and test performance techniques, and they're established for a variety of different kinds of tests on specific hardware, like shock testing of bomb fuses and that sort of thing. Now, one of the interesting things was that a few years ago, the trend was to go away from MIL standards and use commercial procedures, because the folks that were building military hardware thought that maybe the commercial folks knew better what was going on. But as it turned out, the commercial test labs were using MIL specs in the first place, so the upshot of it is that MIL specs are back. And the main MIL spec that we're interested in this area is 810, and it has gone through a bunch of iterations over the last few years, getting specs for more and more different kinds of tests and getting more and more realistic. And actually, the MIL spec 810 has become a pretty valuable and useful document over the years to get you started on doing this kind of testing. Okay, the sort of the opposite of simulation testing is stimulation testing. And what we're doing here is stimulating a failure. And the philosophy here is to use combined environments, vibration, temperature, humidity, whatever. And what we're going to do is make up a spectrum of a random spectrum, and then we're going to excite our specimen, raising the levels until failure occurs. Beef up the failed part, retest, repeat until the environmental levels are high enough. Now, then once we get the screening levels set, then we subject the production items to a calibrated screen, and maybe if we start having field failures, we will adjust the screening spectrum and levels accordingly. Now, needless to say, there are some fairly wishy-washy things in here. So one of them is here. We're using a spectrum that is really not very well controlled. It's a broadband spectrum using my machine that we'll talk about a little bit later. And it's a sort of a brute force approach, and the question is whether we're actually simulating any real failures or whether we're just stimulating the failure that this particular screening level, screening shape is going to produce. So the objective is of the ESS screen is to force as many flaws in the hardware into hard failures as is feasible within a cost-effective time frame. Failures are a desirable result of an effective screen, and ESS is the application of a set of stresses that are designed to stimulate the various classes of flaws. They may or may not have anything to do with what's going on in the real environment. So the whole objective of this is to find the hardware that is bad before it gets delivered. And before this sort of idea came up, this curve demonstrates the failure versus time behavior of devices that haven't been screened or haven't been tested. And the bad news here is that we don't catch very many failures before delivery, and then we catch a lot of failures out here. And so this is the expected operational life, probably the warranty life of the device. And what we want to do is to push the number of failures during the warranty down to a minimum. Of course, if we're a really good guy, we want to push the number of failures out a whole lot longer, but the primary objective right now is to make sure that we have relatively few failures during the warranty period. So if we do some screening, we're going to cause failures here. Most of the failures are going to be caused before we deliver the system. Then after we get some field failures, maybe we'll redesign our screening characteristic so that we get more failures during the testing procedure before things are shipped, and we get very few failures out here in the after the device is delivered. Okay, I've always considered this to be a pretty unscientific approach to the problem, but the fact of the matter is that this sort of thing has produced some very good results in improving hardware before it's shipped. A classic example was that Hewlett-Packard was having a lot of trouble with their early inkjet printers. A lot of them were coming back failed during the warranty period. And these are relatively inexpensive devices, so returns were absolutely prohibitive as far as the manufacturer was concerned. And they instituted shaking and cooking procedures for pre-delivery on all of their printers. And what they did was they actually produced something that looks like the purple or green curves and enormously improved the performance of their machines during the warranty period. So, scientific or not, this sort of thing works pretty well. A simpler one than that is a horror story that I had. We had built this big data acquisition system for the space telescope testing, and about a week before we were supposed to be doing the test, we were operating the system, and I was sitting at the computer, and something went bang. We all looked at each other and said, I wonder what that was. Well, we didn't have to wait for very long, because 10 minutes later something else went bang, and not too long after that it started sounding like popcorn. And what was happening was that all of the electrolytic capacitors that were used for bypass, noise bypass in the signal conditioners were blowing due to old age, or the old age wasn't very old, but the fact of the matter is that there were a whole bunch of faulty capacitors in the system. And if the data acquisition systems had been baked, operated and baked for 20 or 30 hours before it was delivered, all of these things would have been caught. As it turned out, we had a batch of bad capacitors. Every single capacitor in the system was bad. We replaced them all with a panic. Everybody who could operate a soldering iron putting in new capacitors. But the point here is that the manufacturer of that data acquisition system then started baking all of their stuff before they delivered it, and significantly reduced their return problem. In fact, all the hardware we bought from that same outfit after that all operated fine from that standpoint. Okay, so what kind of a spectrum do you subject your specimen to? Well, this is a MIL-SPEC spectrum, and I've forgotten where it came from. But anyway, this is a PSD, power spectral density, is a function of frequency, is low below 20 hertz, rolls up at 20 dB per octave to 0.04 G squared per hertz out to 350 hertz, and then rolls off at 3 dB per octave. And what this is a 6G RMS excitation. It's pretty representative of lots of things and in the world, and it's relatively high. So this sort of excitation is probably going to cause failure in commercial devices if the system is not properly designed. So this is where a lot of people get started. Standard ESS random vibration environment. Okay, extending from that, if it would be really cool if we could come up with a testing system that could do accelerated testing, so that if we do a random test, for instance, at a particular level and find that our specimen survives, can we increase the random level and see how long the specimen survives, and so to reduce the length of testing that we have to do. So there's two philosophies of this: highly accelerated stress screening, and the objective here is to produce screening failures faster than conventional ESS environments. And then highly accelerated life testing, HALT, evaluate the potential life using high stress environment that causes early failure, but can be interpolated to evaluate the true life. And of course, the objective here is to come up with a faster and cheaper method. Both are extremely specimen sensitive. Science is surrounded by a cloud of confusion. This sort of approach should be used with very carefully. What we're going to talk about now is damage potential and prescribed simulation, where we're actually telling an excitation system what excitation function we want to use. So what we need here is a device that allows us to apply any time history, and what this usually means is an electrodynamic or an electrohydraulic shaker, and the question is what we want to make the shaker do to simulate the damage. So time history reproduction is, as it turns out, relatively easy, as we're going to find out when we talk about the control systems. And here we're actually reproducing a time history, perhaps reproducing a time history measured as we drive our car over a Belgian block road or something like that, or reproducing some sort of an impact, a shock, where we're actually reproducing the time history. Spectral energy simulation is the one that's used most of the time, and here we're using a shaker to excite the specimen to a specified PSD. And the question there is, the problem there is, as we've seen, a specified PSD can have any number of time histories. Then the shock damage simulation will use a shaker to excite the specimen to a specified shock response spectrum or some other characterization of the shock. And the question there is what time history do we want to use? So, given that we have a machine that can reproduce the time histories, how are the time histories specified? The objective is to provide a conservative motion history that includes all of the important excitations. And options include reproducing the measured time histories, and that's the most realistic if the flight history simulation is repeatable and realistic. Then the other possibility that we talked about in the earlier slide is reproducing the spectral magnitudes, excite failure mechanisms that are sensitive to input frequency. And how do we define the spectral magnitudes? And the other possibility is reproducing shock spectra. So, question here is our test transient or continuous? So we're going to break the discussion into two categories: transient tests, and the definition of transient is that it begins and ends in a quiescent state and has a relatively small number of cycles. Another possibility is a continuous test, and this is one that goes on for a long time, whatever that means. That may mean 10 seconds or it may mean 1,000 hours. So transient tests are performed with drop, impact, or programmable machines. The objective is to reproduce damage or real events, and the method is drop test, reproduce a half sine amplitude and duration, and we'll talk about machines that do that. Perhaps we'll have an impact machine. We'll talk about machines that do that, that reproduce a spectra and time envelope. And then the other possibility is programmed, where we use an electrodynamic or electrohydraulic shaker to reproduce a design time history. And Chapter 6 is going to cover how we design that time history. A continuous test is where the excitation functions are random or sine or hybrid. Hybrid is sine on random, random on random, transient on random. Lots of possibilities there. And these are performed with a programmable or multiple impact machine. The objective is to reproduce the damage of real continuous events. The limitations are that peak response levels are low for the power available. We can't, if we're doing a random test, we can't put a lot of energy into one particular frequency as contrasted to sine testing. The methods are programmed, reproduce a really designed history on with a shaker, or multiple impact, reproduce an ESS environment. We'll discuss these operations in Chapter 7. Then a continuous test like sine. What I'm showing here is a sine sweep, and it's performed with a programmable exciter or perhaps an eccentric mass machines. We don't see many eccentric mass machines anymore, but if we're shaking a skyscraper, maybe that's one of the options that we might use. The objective is to provide a high level or easy to understand result. And the point here is that a sine test puts all of the energy into one frequency, and so we can really beat the heck out of the specimen. And if we have a failure with a sine test, we know precisely what frequency the failure happened at, and so we've got some very good tools to get some understanding of what actually happened. The big problem with it, of course, is that there's not very many things in nature that are sinusoidal. An exception to that, for instance, is an out-of-balance wheel on your tire or something like that on your car. And so a sine test might be a good simulation of that. The methods to do sine testing are programmed using electrodynamic shakers, and we design and we make up a desired spectrum, and we program the spectral amplitude as a function of frequency, and then the eccentric mass is very rough or cheap tests. And then, of course, we've got hybrid tests, and there's lots of those that have been developed over the years. They can only be produced with programmable machines, and what we're trying to do is do a real simulation of real events. And the peak response levels are low for the power available because it's mostly random. And what we're going to do is reproduce real or design spectra with a periodic function superimposed, like sine on random or transient on random. Here's a time history of sine on random, and what we're seeing here is that we've got random with a sinusoidal bang in it at this particular frequency, and it's hard to tell whether this is a different sinusoid or whether it's a piece of random that just happened to be that high at the time. But this is a good simulation of helicopter behavior, where we've got a lot of sinusoidal input or sinusoids with harmonics, which this point right here may well be. Okay, so the next step is to measure the responses, the accelerations, forces, or whatever, to evaluate how well the environment is being reproduced. And we will do that in the next chapter. Thank you for listening.